box. There's a spring on this side. And that's K1, and there's a spring on this side. K2, these are both mounted, and this is oscillating back and forth. And they asked the question differently than I asked the question, which was, they say, show that the frequency is equal to the root of the frequency of the first one squared plus the frequency of the second one squared. We did part of this problem already. Can I use that, which we did in class, as a springboard for the rest of this? So we have that the frequency of oscillation is going to be equal to 1 over 2 pi times the root of m over k1 plus k2. I already know that. Bless you. Bless you again. So frequency 1 is going to be 1 over 2 pi times the root of m over k1. And frequency 2 is going to be 1 over 2 pi times the root of m over k2. There is probably a more elegant way to do this, but you could just solve both of those for k1 and k2 and sub in here and see if you get that. That's all I would do right now if I was to perform that problem. But like I said, there's probably a more elegant way to do it. Yep?
Wouldn't the flip the radical, because of that time period?
You're right. It's k over k. It's k over m. I'm writing frequency, but I mean period. I'm sorry. I'm writing period, but apparently I mean frequency. I don't know what I mean. Sorry. That's what it should be. It should be that. So, I'm thinking, it's not elegant, but I'm thinking substitution's the way to go. And I would say the same thing for question 75. Substitution's the way to go. So I'd argue that you guys can probably do 75 on your own now that you see what I would do here, because we did 75 the other way too, right? So when you had two springs in tandem, you got a different issue for the frequency. It was not glamorous when we did it in class, but you could do that as well. So I'm going to leave that there and say that we're done with 74 and 75. So all right, look, there are 15 minutes until they're going to release for club. Let's take a look at this, all right? Because I want to make sure that you've had adequate chance to look at. Probably not as much time as I would have liked, but we'll get started. I think question A should not have been a difficult problem for you. Everybody should have gotten the points for A. If you had difficulty with it, I have concerns. I probably would have just done V equals the square root of, it's 2h over g? No. What am I doing? It's asking how fast it's going when it first strikes the spring. So did you do 1/2 mv squared equals mgh? Because that's all you need for that one. So cancel the m's, and v is the square root of 2gh. That gets you the velocity when it's here. So hopefully that wasn't a problem. By the sound of the room, I'm concerned it was. Question B, determine the period of the simple harmonic motion that ensues. You don't need anything to do that outside of the definition of period for a spring mass oscillator. So question B is self-contained. It wants period, so we're talking about 2 pi times the root of m over k. That is on the equation sheet. You have 3 equations about simple harmonic motion on the equation sheet. This is one of them. The other one that's on the equation sheet is the period of a pendulum. And the other one that's on the equation sheet is 2 pi divided by omega. That's all that's on the equation sheet. So everything else you have to keep in your head. Physical pendulum, probably not a bad idea to memorize. So I don't want to go into that one. That one's pretty straightforward. They gave you the mass, they gave you the size of the spring constant. Put it together. Question C is the one I knew I would get you on, because I think most people don't think of it that way. They think it's going at its fastest when it touches the spring, and it's not. It's going its fastest after it reaches a point where the net force equals 0. This is how far the spring will be compressed. This also establishes where equilibrium is. So you're asked about the amplitude in a minute. This establishes where equilibrium is. I'm assuming that it's going to compress the spring, I don't know, some distance to make it to equilibrium. And you're getting that from here. But it's going to oscillate back and forth beyond this position, which is why D exists, the maximum compression of the spring. That's a tough one. There are at least 2 ways I can think of to do it. One is to use some information we know about oscillatory systems. Like you could probably use Vmax. Whoa, I don't know what that was. Vmax equals x naught times omega. You could probably do it that way. But you don't find Vmax in the problem. They ask you where Vmax occurs, but you weren't actually asked to find Vmax. You follow what I'm saying? But you could do that and solve for x naught, which would be the amplitude. You could also find the maximum compression of the spring directly without finding the amplitude. If we get rid of all the distraction that's here, the maximum compression of the spring occurs when the box is brought to rest. So there's going to be some position where the block is brought to rest. Hold on just a minute. Yeah. Say it's right here. So the box has gravitational potential energy here. And down here, it has elastic potential energy. You don't know what this height is, nor do you know this distance. But mgh has to equal 1/2 kx squared. It's a conservation of energy problem. H equals 0.45 plus x. Right? Have I solved it for you? If not, I'll go one more step. Solve for x. You have all of the other variables. You know the mass, you know k, you know g. Solve for x. There are 2 possible answers, apparently. It's quadratic. If they both make sense, we might have to work that out. And trust me, if there's a second answer, it will make sense, but it'd be impossible to happen. Try it. See what 2 x's are. You guys have them fancy adding machines. I don't. You see how I'm doing this before the test? Bless you. I don't know, does it factor? Oh, it'd be so cool if it factored.
You multiply it. K is 200, 1/2 of 200 is this.
I don't know that it factors. I would have to do quadratic. I'm waiting patiently. Come on, we're gonna call club soon.
Oh, do you want the answer?
Yeah, I want the answer. I want x equals. It's gonna be two of them.
0.416 and a negative number that I didn't.
I want them both.
Negative 0.21.
Negative 0.21. All right, so my two answers are point what?
416.
And negative 0.21. All right. So, why are there two answers?
That's what's up for tracking.
Oh, come on. That's such an AP chemistry answer. Yeah. What?
Spring can go the other way.
That's right. This would be the other possibility if the spring could rise up to meet the mass. Now, it can't do that, right? The spring, but if you stretch the spring out to this position, then we would also be at a place where the mass is zero, which is telling you something. Notice this is twice as big as this. It's oscillating between these two places. Do you understand what I'm saying? Wherever the equilibrium position was that you found in question C, it's oscillating, I bet, 20 centimeters above and 20 centimeters below. And 20 centimeters below is a total of 40 centimeters. Now, if you want to find out what CE is, determine the amplitude is the difference between the equilibrium position and the maximum displacement of the spring, which I bet works out to be 20 centimeters. Or 21 centimeters. I don't know. I didn't find the equilibrium point, did you?
It would be like 0.1 or something, that's usually that.
So it's oscillating between those two. I guess you're right. The total distance it's oscillating is 60. That's right. 40 plus 20. That's the total oscillating distance. So your amplitude turns out to be 30. Tough question, eh? It's not tough once you know what you're doing. But I don't think you guys would have gotten D without thinking about the energy. Now, there's another way to have done this, by the way. You could have broken it up into steps and figured out how much kinetic energy it has when it touches the spring, and then did the problem again as a conservation of energy problem. There's also a way to do this problem using simple harmonic motion, but I believe it's harder. I think this is the most direct way to do the problem. Which brings, this has a submission button. My expectation is you will complete the problem, go through the whole thing again, and make sure you submit it today. You've seen it performed for you. You work it out now. I used to just say, okay, we've done it together and you all had done it. No. So my expectation is you will submit your answers to this question. Okay? I'm just going to give you some class, you're going to want these class participation grades. So make sure it gets turned in. Yes, ma'am?
Oh, it doesn't actually have
I'll make sure the submission one shows up. I just put it out there now to make sure that I get it in front of you. This question, by the way, tonight you're going to be given this question. It's the one that was given to next year. And I'm going to want you to set your timer for 15 minutes and try it. It has many of the same questions, but it has a wrinkle. And you know they're all going to have a wrinkle. In this one, you'll notice that there's two blocks placed on top of each other. And it is started at the relaxed position of the spring. That's where they release the system. And they also talk about pulling it down and releasing it. They ask several questions, but one of them is how far can you pull the weight down so that when it oscillates, this box doesn't leave the surface of the bottom box. You want them to not separate. I'm going to give you a hint. So if you want to draw a quick picture of this, I want you to have this hint. It should be enough to help you solve the problem this evening. The hint is this. The only way this box stays in contact is if the acceleration of this box is never greater than g. If it accelerates downwards at an acceleration greater than g, since they're not attached to each other, they'll separate. So you need to ensure that the A max of this problem is less than g. That's how you figure out what the max displacement can be. That's a solid hint. But we've seen problems like this. The friction problem you had in the homework was similar. You had to know what the threshold was. And in both those cases, it was based on force or acceleration. All right. You guys who have your